Okay, let me start thanking Thomas, who is not here in this audience, unfortunately, for inviting me for this collaboration here in this very beautiful place. I like it very much and enjoy very much my time here. So as you see from the slide, I come from Torino. So Torino is a city placed in the north of Italy, not far from Milan. And in this picture you see the most iconic building of Torino, which used to be a synagogue in past times. And now it hosts a cinema museum, which is very nice to visit. And actually is ranked among the highest buildings in the world, though it's not very high, but it's the highest building in the world made of masonry. So it's not made of concrete, but of bricks. It is the highest in the world, and it's also the highest museum in the world. So if you, the rankings is very surprising also for me. Okay, apart from these less scientific aspects, what we do in our group that is called the Theoretical Chemistry Group of Torino, since more than 40 years we developed computer codes for the quantum chemistry of crystalline solids. The two main codes that are developed by our group are the Crystalline code and the CRYSCOR program. And my talk today will be sort of an overview of everything that is going on recently on these two codes. So sorry if it will be a very packed talk, but we couldn't decide a single topic. So also Thomas asked me to make a broad introduction of several things that can be of interest to several people. The persons having a permanent position in our group presently are listed here in this picture. So there is me, the head of the group is Roberto Rovesi, who will retire actually this year, at least officially, though I think he won't retire from science. And then there's Alessandro Ebba, Bartolomeo Civalleri, Piero Liego, and Silvia Casassa. These are the people mostly involved in the code development, and there is also Anna Ferrari, who is a researcher more dedicated to applications. The crystal code is a crystal devoted to the Hartree-Fock and DFT treatment of crystalline periodic system. So its particular aspect with respect to other code is that it uses a basis set made of Gaussian functions. So most well-known codes for periodic and crystalline systems do use plane waves, usually. While since the 70s, when the development of the code started, the strategy was that of really using the quantum chemistry, machinery, and techniques with the basis set of Gaussian functions, and use that for treatment of infinite periodic system, which is, I would say, very complicated, but it was thanks to really great ideas that came out in these early days on how to deal with this problem, that it is possible to do it, and it turns out to be also very efficient in a number of aspects that I will show you. So it's quite an old code, going to turn 50 years now in development, and it's sold in about 400 licenses all around the world. The good thing is that we really can use the same machinery, same language as in the molecular codes. And with respect to the plane waves, this allows for very cheap hybrid function and a Hartree-Fock. So the cost is just slightly higher than for usual function, as well for plane waves. This becomes very costly, even hundreds of times more costly to do hybrid function. We can really deal with reduced dimensionality, so we can really do two-dimensional, one-dimensional systems with the zero dimension, so we can do molecules and we get exactly the same approach as in molecular code. So it's exactly molecular calculation. But with plane waves, they are bound to defining a unit cell in 3D, so they can make molecules only by defining a large unit cell. Of course, some drawback is that we need to define a basis set, like for molecules, while plane waves are very nice. Does this work now? Yes. But what people like about plane waves is that you just have a cutoff and a single number, a single
threshold defining the precision and no basis set. So sometimes people complain about having to deal with what a basis set is. So this is a last presentation paper we made for the last public version that was Crystal 14. We are going to come out with a new release this year, so we were preparing a new presentation, a new version that will be released in this spring. We are making schools to teach how to work with the code around the world. So the next schools we will make will be in Minneapolis, hosted by Laura Gagliardi, and in London for this year, but also we had schools in Brazil, China, India, and a lot of places. Okay, so generally Crystal has a really lot of features, but the main accent that we have put in the recent years is about simulating vibrational spectra, response properties of crystalline materials subject to external electric fields, and some really great accent on the robustness of the code and in going to massively parallel, really exploiting the big facilities that we have available nowadays. So this will be more or less the topics I will focus on in this first part of the talk. And then I will try to also say something about the CRYSCOR code, so the local correlation part. So about the massively parallel crystal code, the main people developing this have been Ian Bush and Roberto Orlando. Unfortunately, Roberto Orlando left us just this year, so this was a quite big hit for our group. And anyway, the idea behind this development is to really exploit the power of modern computers. So we are not anymore dealing with these computers that you can see on the top left, but we are nowadays something that has a huge power. So we really want to exploit this huge power offered by modern computers. And we want to do it not with other methods that are specifically developed for big computers, but just bring the standard DFT methods to the big computers. So to do the usual calculation for bigger systems with bigger resources. We want to use the hybrid functionals. We want to do all the properties and also exploit the symmetry of the system. You know that crystals have always a high symmetry, and being able to exploit this high symmetry is quite beneficial to the calculation. Our code is installed and running efficiently on a number of infrastructure, so this is a bit outdated slide. Most of these computers have been renewed, but we are working to reinstall everything on all the facilities in Europe and around. And just an idea of what can be done, what are the boundaries of big systems. So we are hitting actually the boundaries of biochemistry with the size of the system that can be treated. For instance, an interesting application is this application of drug delivery through this silicate that is called MCM41, which mimics an amorphous system, which is amorphous on the short range, but has a structure on the long range. So has some mesoporous holes where you can actually put drugs and then they can be delivered in the body. From the point of view of the calculation, this is very challenging because in order to mimic something that is amorphous on the short scale, you need to make some big supercell with a big amount of atoms in the unit cell, but this was successfully made by Piero Liengo and his co-workers, and they actually managed to simulate an infrared spectrum of this system and compare it with the experiment and see that actually the model is validated. And we also could use this to test the scaling of the code and see that if you make a cell and a calculation heavy enough, you can reach 90% accurate speed up, so 90% performance up to 2000 core. Actually, I don't have the slide, but we reached also success of making the code running on 32,000 core and getting the same numbers, even though the efficiency is not as good as in this case because there's some work to be done. So then one can put the molecules into these holes, optimize the structure, see where these molecules are going. We don't have molecular dynamics, but we can make just geometry optimization, and each step in this calculation is less than 10 minutes. So one can actually optimize the whole structure at the full quantum mechanical level within reasonable time. And then one can also compute vibrational frequencies and compare with the experiment and see that the frequencies of stretching of this unit of this CO stretching band is actually comparable with the experiment, and then validate this as a model of the system that is actually created in reality. Other calculations have been done on crystal of proteins. This is probably the simplest protein one can calculate, which is a crumb bean protein, but still it's a crystal. This is very big system from quantum chemical point of view. And it was possible to compute the full vibrational spectrum of this crystal without, with a good accuracy, so that there are no negative frequencies in this calculation, which means that nothing went wrong in this big calculation that took 200 hours, so a few days. Last example of a big calculation is this metal organic framework, which is sort of giant. In fact, that's its name, this MIL 100. And it was possible, thanks to a praise grant that Bartolomeo Civalleri got, to compute actually absorption of molecules and properties of this big system with about 300 atoms per unit cell. Okay, so first part was about massively parallel code. The second part, since I know that in this CTCC a lot of people is involved in linear response properties, I wanted to say something about the recent developments. The main people working with me in this direction are Michel Hérard from France and Bernard Kirtman from Santa Barbara in California. And of course this was also a big topic in which Roberto Orlando gave a lot of contribution until he was active working. So, of course, linear, nonlinear optical properties can be obtained as a derivative of the total energy with respect to the electric field, then taken at zero field. What is peculiar when we are dealing with the periodic system is that the electric field operator is not anymore the same operator that you have for molecules. The reason is simple, is that the operator that is just, the molecular operator that is just the field times the position, he is not consistent with periodic boundary conditions. So if you think of a periodic system that is repeated and then you plot this operator, this just breaks the translational periodicity. So you can't use this operator as is. This actually was a fundamental problem not solved until late 90s, when Vanderbilt and others elaborated the form of this operator, which is the one that you see here in the bottom of the slide, which is the usual field times a more complicated object, which involves a Fourier transform and a derivative with respect to the reciprocal space vector K. This works very well, but complicates everything, because as you've seen in the previous slide, we want to take first, second, third, fourth order derivatives. Now we have another object which is another derivative, which brings everything to a further order of differentiation and mixes with other derivatives. So all the formulas become more complicated. Also, the form of this operator is particularly complicated. So one tries to put it into matrix notation. One can deal with this derivative with respect to K in the usual perturbative approach. So to describe the derivative of coefficients as the coefficients unperturbed multiplied by perturbation matrix, which is represented by this Q matrix that you see here below. The fundamental problem is that this Q matrix has some diagonal imaginary elements which are ill-defined. So they are defined apart from an integer which is a representation of the fact that the electric properties of a system depend on the boundaries, how you cut the boundaries. And so since you don't specify the boundaries, the system is infinite, there is an arbitrariness in the definition of this quantity. Luckily, all the physical properties that one can compute out of this operator should not depend on this element. So one check that the formalism is right is that these elements don't appear in the final expressions. But this is, I tell you, very complicated when it comes to higher order derivative. So this development comes, actually our group worked now for more than 10 years in the development of this coupled perturbed method. So the equations were derived where these are, look very much like the usual coupled perturbed equations, apart from that you see some derivatives with respect to the lattice vectors which appear additionally. Since we have a more complicated Hamiltonians, we will have even more complicated equations and more terms. But apart from that, the idea is the same of the usual coupled perturbed approach. This was very effectively implemented, also thanks for the DFT part with the collaboration with the Tromsø group for including the X-Chiffon library for the derivative of the functionals. That is what we use still today. And this is an example of a very recent application we did of a linear chain of a phenylalanine radical, which is a very interesting system for non-linear optical properties, which was studied by Nakano and Benoit Champagne. So we also wanted to see what happened in our case. And this forced us to implement actually the second order hyperpolarizability for open shell GGA functionals, which is something that took me quite some mental sanity to implement in the code. And then I wanted to check if the implementation was right, and I wanted to check some molecular code that was implementing it, and found that actually nobody else ever implemented it, or at least all available version of the codes, Dalton or any other code, doesn't have this for open shell GGA functionals. So this made me quite proud that I kept my mental sanity through this development. And what we found interesting in this system is that actually you can see how the results converge if you make a dimer, tetramer, pentamer, and so on. You make oligomers, and you find that results are quite far away. So you really can't reach convergence on this second order hyperpolarizability by just making oligomers. You really need to do the full periodic calculation, because otherwise you really make a very poor estimate of the properties of this system. Of course, this is a model system, so it's not a real-life system. It's sort of a toy system where to check these kind of properties. But it was very interesting for us to see that here you really need periodicity in order to correctly describe these response properties. Another property that we implemented recently is the dynamic first hyperpolarizability. That is a very interesting quantity for solids, because if you take it with a given choice of the frequencies, that is, so when you have a third order derivative, you have three fields, and then you can choose three frequencies. Three frequencies means that the sum of them should be zero, so you have two frequencies to choose. There are several possible choices. The approach is general, but there are some that are connected to some physical quantities. And this choice here, minus 2 omega, 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 is the second harmonic generation, which is the process when you send some light into a sample, and then you receive light which is doubled frequency. Or the Pockels effect, which is more connected to the beam. For instance, so we implemented this approach, which was also not very easy to implement, but in the end it's quite successful. So we tried to compute, for instance, the second harmonic generation property of this molybdenum disulfide, which is a very interesting material. And this is a very powerful technique because this material is very sensitive to the number of layers. So people are producing this layered system and they want to know how many layers are there. And a very good way to measure it is to check the second harmonic generation response, because it's very different if you have 1 layer, 3 layers, or 5 layers, or if you have an even number of layers by symmetry, this becomes 0. We could compute this and compare with the experiment, and you see here that our estimate is really matching this trend, though we can try to make it better by improving basis sets or trying to push change some function. And this was just a first try. It was, in my opinion, extremely good as a first try on how it works. Another interesting application of this second harmonic generation is the application to, for instance, molecular crystals like urea, because this technique is used to spot pharmaceuticals into a matrix. So, for instance, if you make some pharmaceutical pill and then you want to know where the active principle is inside this matrix, you can use this technique. And the pharmaceutical often is responsive to the second harmonic generation, while the matrix embedding it is not. And then you can make a picture of this kind. And then, for instance, we took urea, which is a prototypical molecular, and managed to compute and compare with experiment the response of the second harmonic generation tensor. Okay, I will skip a bit because time is running, of course. And another chapter about this, what we recently worked on in Crystal is the simulation of vibrational spectra, which is also closely connected with this response theory, because what we did in the recent years was to implement the analytical intensities for infrared and Raman spectra. And this is also done by a combination with the gradients and the coupled perturbed approach. Again, the equations become horribly complicated. They are already horribly complicated in the molecular case, but here we have all these complications I said about this derivative with respect to the lattice vector. And then we have to take care that through all these complicated equations, these diagrams of these terrible Q matrix cancel out precisely, and it was a long work to figure out actually the right formulas where everything was done in the correct way, but now we got them. First thing we did, and this is something that is a very powerful way of checking things in our approach, is to try to see what happens. For instance, if you do a molecule, you can compare with the molecular code. Then you make an oligomer, you can still compare with the molecular code. Then you make an infinite polymer and see when the oligomer converges to the polymer. The polymer infinite you can't do with the molecular code, but in this way you validate that. Then you start stacking polymers. You put polymers one on top of the other, and at some point you converge to the slab. Then you start stacking slabs, and at some point you should converge to the bulk. This is a very strong way of validating the numerical accuracy of this kind of methods, because you start with comparison with the molecular code, which is supposed to be right, and then you can go all the way to the 3D crystal, and if all the steps are correct, then you're sure that your result for the 3D crystal is correct. We did this, for instance, for the Raman tensor, and checked that actually you need, for the lithium fluoride structure, you need 75 lithium fluoride units before reaching 4 digits in accuracy. Then you need 150 stacked polymers to make a slab. So you think if you had to make the same property with this precision just by a big cluster, you would need a huge amount of atoms. While for the bulk calculation, it's just 2 atoms per unit cell, and you do it just in nothing. So this is a very powerful validation of our approach. And now I want to show you these calculations we did for this system, which was created very close to here. In fact, it's called UIO, University of Oslo 66. And this is one of the metal-organic frameworks that is developed by Carl Peter Lillerud and his colleagues here in Oslo. They have a very strong collaboration with a group in our department led by Silvia Bordiga. So here people are synthesizing these new metal-organic frameworks, and in Torino they are making the Raman spectra to characterize these solids. And so when we developed this, they asked us, can you simulate the Raman spectrum of this? I said, wow, okay, this is the ultimate challenge because this is a complicated system. Let's simulate the spectrum. And I did the calculation, and actually what I got is very good. Actually, if you see the peaks are there, I didn't perform any shift of the calculated frequencies. So this is just as it comes out. If you shift it a bit, you even get better accuracy. And I was very happy. So I put this on the paper presenting this result as a final answer. Everything is working good. And actually, people from Journal of Chemical Physics even liked this picture. Even I have nothing to do with the invention of this metal-organic framework, but they wanted to put this picture on the cover, and okay, how to complain. And but then you see, okay, this agreement is good, but you can see here not exactly all the peaks are the same. So we thought, okay, there might be some problem, functional or basis set or whatever. Okay, let's not work too much on this. It's already very good. But just a little time later, Lillerud came out and said, wow, I found a better way of synthesizing this. This was full of defects. Now I can synthesize it really as you model it. And then with this experiment, he managed to match our calculation. So you see now all the peaks in all this area is just, I mean, if I draw it by hand, I would make a worse job, right? So it's just exactly all the single peaks, apart from the baseline that goes up, they're exactly the same vibrations. So this was a really surprise to me that it was the experiment that was wrong, not the theory, at least for once. Okay, so this was the overview over some of the recent developments of the properties of crystal. Now I will spend another few minutes about the local correlation in CRYSCOR, which is actually the main point why I'm here for collaborating with Thomas. And this project of developing the CRYSCOR code actually is now we used to say this is a younger code, this is a new project. Actually, I figured out it's 15 years we've been developing this CRYSCOR code, so it's not so young anymore. And this started a collaboration between Cesare Pisani in our group and Martin Schutz, who at the time was in Regensburg. Now he recently moved to Berlin, to the Humboldt University. And here you see the main people who worked on the CRYSCOR code during the years. The main developers are me and Dennis Uzviet. And the idea is just to implement the local correlation methods as they have been developed proposed by Peter Pulai in the 80s, and then implemented, for instance, in MolPro by Martin Schutz and Joachim Werner, just to implement these methods, these ideas for the periodic system. So to bring into the periodic system this very same idea of the local correlation methods. The idea is that the occupied space is localized, for instance, in our case, obtaining Wannier functions. And the virtual space is not obtained by localizing the Hartree-Fock orbitals, but rather obtaining other orbitals, which are projected atomic orbitals, which are obtained by projecting out the occupied space from the AO basis. In this way, you obtain a set of functions that span the same manifold, but they are non-orthogonal. So you have to deal with the fact that these functions are non-orthogonal. But they are very well localized, so that we can have an occupied orbital that can be assigned to a region of space and define a virtual space that, instead of being the whole molecule, the whole system, is just restricted to a vicinity of this orbital. And also in the integrals that you have in post-artifact methods like MP2 that involve pairs of orbitals, you can restrict the pairs of orbitals to the two orbitals that are distant up to a certain distance. Since you can assign these orbitals to some region of space, you can restrict these summations. This is a key aspect when you have to deal with an infinite system, because the artifact orbitals of an infinite system are totally delocalized over the whole infinite crystal. So you cannot, while for a molecule you could do a canonical method and use the whole system, for a crystalline system you can't just use the whole system. You need to win over periodicity. The good thing is that if you can localize an orbital, then you can assign it to a unit cell. And then you can restrict your calculation to the unit cell, that is the periodic repetitive unit of the system. Then you can select the virtual space around this object, and also the other local orbital which pairs with it can be restricted up to a distance, which turns out to be not much. We usually use 12 angstrom. This means that by describing a sphere of 12 angstrom around the unit cell, you actually describe your whole infinite system, which is quite a big win. So we implemented, we worked on this CRYSCOR code for quite a long time. So as of today, we have implemented the local MP2 approach. We have also a local MP2 implementation that exploits the F12 method for explicit correlation. We have also local CI singles code for which is the first step in making excitation and band gap corrections. So we have a number of papers that have been published through the years for the developments. Of course, we take the artifact solution from Crystal, and the idea is to really make something that is black box and usable, and that people would actually choose to use MP2 rather than DFT when convenient. So we want to challenge the cost. Of course, it's hard to challenge the cost of DFT, but to make something that is not totally out of this world when one wants to do an application. We managed through the years to apply this to several kind of applications: molecular crystal, rare gas crystals, absorption of molecules, relative stability of crystalline phases, nanostructures, nanotubes, several things. One winning point is that we, through this separation of according to distance, we can establish a hierarchy of approximation for the calculation of integrals, which speeds up incredibly the calculation. So in this sphere that I said of 12 angstrom, we can have a first part where the integrals are approximated by a density fitting approximation. Then there is a part where we can use a multipolar expansion, and then for the long range we can even extrapolate to infinity, because we know that after a certain range we have r to the minus 6 decay, and then we can just extrapolate the contributions to infinity. So in the end we have a real local approximation in principle. Density fitting is actually the key to the speed of all of that. This is a table from our paper of the implementation of the density fitting. This is, I'm not going into the detail of what the density fitting is. Essentially, we're expanding the 4 index integrals as 3 and 2 index integrals into an auxiliary basis. And this allows, for instance, for a calculation on diamond to go from 16 days of calculation to 4 minutes. You can understand this is quite a big thing. So you go from not doing the calculation to do it without thinking about it. And this is now very effective and very robust and works very nice. I also made a parallelization of this code, which is quite good up to 50 or 100 processors, and allows to deal with, say, 100, 150 atoms per cell without too many problems. So in one day or so you can compute system with 150 atoms. The problem we had until a few years ago, which is a general problem for these local methods, is the definition of the virtual space and the definition of the truncations of the local method. Because in principle, you need to have control over all this truncation by yourself. So the code requires that you define this truncation in a way that the approximation is not giving you wrong numbers. This can be very difficult for big systems, and especially can be difficult for people who have no big experience with local correlation. This is a reason why these methods didn't actually break through the wall of mainstream calculations. So the recent developments we made are in the directions of making it more black box and usable. First thing, we have implemented a screening of occupied pairs, which decides by its own when to do density fitting, when to do multipolar approximation, and when to neglect the pair. And this is based essentially on an idea developed by Daniel Katz and presented just a couple of years ago on JCP, which is a very simple but effective idea of estimating the mutual penetration of the two Vanier functions as a product of the atomic populations, and then use this criterion to screen what is the overlap actually of these two Vanier functions. In this way, while the decay of the contributions can be very different, here we have two systems that are carbon dioxide and germanium, you see that this is the decay of the contributions to the energy of different pairs at different distance, and they behave completely different. So you cannot tell a recipe that is universal just by defining the distances. While in this approach you have just a single criterion, a single parameter that you can tune, so you can strive for accuracy rather than for setting some distance, and then the two very different systems behave in the very same way when this threshold is considered. So you can really set this threshold to somehow between 10, somehow about 10 to the minus 6. This will work equally well for any kind of system which is polarizable, not polarizable, and so on. The other big step we've made is to implement a different definition of the virtual space, which is the orbital-specific virtuals. Just to give you an idea of what this thing is about, is like when you are preparing a dinner and you invite for dinner at your place a couple of friends. And then if you invite a couple of friends, you can ask, what would you want to eat? I want pasta. What would you want to eat? I want meat. And then you can prepare pasta and meat and serve them what they most like. And this you can do if the guests are two. But what if you invite 100 of guests? You cannot ask each of them what they would like to eat and then go and shop for each of them and prepare exactly the meal they want. You will prepare a buffet with a good variety of choice, and then each one will pick what he likes most. This is exactly what we need to do for the local correlation. So we don't want to define excitation domain for each individual pair orbital, but we want to offer a choice of domain, and then each orbital chooses the virtual space he likes the most. This is the idea behind two approaches. The most well-known is the one of called pair natural orbitals, which is the one that is used now very effectively in codes like ORCA or MolPro, and it is very effective especially for couplet cluster. And there is another approach, which is orbital-specific virtuals, which is actually an approximation to the pair natural orbitals, which was, I've been told, was originally proposed by Peter Pulai, but there is no proof, clear proof of that. And then it was again proposed by Garnet Chan and Fred Manby a few years ago. The idea is essentially to make a very simple MP2 calculation. In the case of orbital-specific virtuals, this is done only on diagonal pairs, so only on orbitals on the same center. And then this trial calculation is used to generate new virtual orbitals, which are then weighted according to their contribution. So there is a diagonalization of the amplitudes obtained in this calculation. And then one can set once a single threshold for accuracy according to how much of the electron correlation one should recover. This sample calculation is done on very big domains, so one sort of goes toward the canonical, so going beyond the local approach. And then locally these orbital-specific virtuals are created and then used by combining the projective atomic orbitals. So in the end, these will be orbitals that are dependent on the occupied orbitals, but not on a domain. Okay, so this is a bit complicated plot, so I will just tell you the bottom line and ask you to trust me. So what we found out is that actually we can get a much better accuracy at a much reduced cost. So in the end, the overall calculation, the trial calculation plus the OSV calculation with MP2 will be way much cheaper than the original calculation, but with a much better accuracy. So we recover a much larger percentage of electron correlation. And okay, a couple of years ago we published this paper of the implementation. Now we have done some benchmarking that this system that I showed you with the PIO implementation was taking 1 day on 48 processor. It's now taking 2 days on 1 processor. I'm yet to finish the parallel implementation of these OSVs, so this will be a few hours probably in parallel. What is also good is that now you don't have to bother about the changing size of these domains. So we can actually try to do numerical geometry optimization because the potential surfaces are smooth automatically, just without any intervention. This is an application we did last year on black phosphorus. So we wanted to estimate the exfoliation energy of black phosphorus. And as a first thing, we needed to optimize at the MP2 level the structure of the bulk black phosphorus. And we managed to do it by making all the points of different geometrical parameters and fitting these by a paraboloid and extrapolating to the optimized geometry. And we managed to estimate the exfoliation energy of black phosphorus, which you know is very hot material because if you exfoliate black phosphorus, you get phosphorine, which is one of these post-graphene materials, these 2D materials that people like so much nowadays. This also makes an interesting story because we did this very accurate approach. Actually, we did the MP2, then we estimated on clusters what is the contribution of higher order. So we made molecular couplet cluster, single, double, triples, quadruples, and estimated all this complicated contribution and estimated that the exfoliation energy is 150 millielectron volt per atom. That was accepted, Journal of Physical Chemistry letters, everybody happy, wow, the best approach ever. Just at the same time, another paper came out on nanoletter by another group who did diffusion quantum Monte Carlo, which is yet another very accurate approach, which is supposed to be also the best accurate approach, and they got just half the energy for the same thing. So just instead of 150, they got 75. Which is totally puzzling because you have the two most possible accurate approach for a solid state which give one double than the other. What is even more puzzling is that we compared with DFT-D3, and DFT-D3 confirmed the same data for us. They compared with DFT-D3, and their DFT-D3 calculation confirmed their result. And then we said, okay, what's going on? Turns out that in the DFT-D3 you can have damping that can be the Beck-Johnson or not. And these changes, just in the DFT-D3 changes this number from one to the other. So they are both DFT-D3, but this damping parameter changes this result. Who is right, we don't know yet. We are investigating, so we are doing further calculation. We found that actually we are overestimating actually because if we do, now we have RPA, so we are doing RPA instead of MP2, and then further correction on RPA, and we discovered that MP2 is estimating the long-range correlation energy. So we think the best estimate we have as of today is 120 maybe, but still 75 is quite far away. Other example of application, we did this relative stability of silicon clathrates, which are very big, strange structures made just of silicon. And this is the kind of system where you wouldn't expect dispersion to play a role because it's all purely covalent system. But if you look at a delicate quantity like relative stability, then it makes a difference. So if you don't take into account any dispersion relation, you see you get one kind of relative stability. This you see on the x-axis are all different structures, the different of these different polymorphs. If you take into account dispersion either by MP2 or DFT-D3, you get a totally different picture of relative stability. So in this system, really, you need to take into account this dispersion or these dispersive forces. What is interesting from the technical point of view is that we managed to do this whole set of calculation without totally black box. So this was done by Antti Kartunen in Finland, in Helsinki, and I just gave him in the code. He ran everything without problems and said, okay, I have the numbers, totally black box. So this, for me, is the proof that actually this new version of the code with the orbital-specific virtuals is really effective. Okay, I'll maybe skip over this further application. So conclusions. So I've tried to convince you that Crystalline and CRYSCOR are two wonders of the world, and we have a lot of ongoing projects. So we are really trying to keep up with the work and implement new features. So acknowledgements to all the group in Torino, the former members of our group, and other authors and people around the world who contributed to this development. And of course, I thank you for your attention to this seminar.
Thank you very much for a nice presentation. Questions? Prima?
Yeah. One first, you did this, you said they converged, was it hydropolar?
Yeah.
Very slowly as you extend.
Yeah.
So I remember about 10 years ago we looked at polarizabilities extending. And then it was, if you look at group polarizability in a sense, you add one more system and then you get the added polarizability. So that converges like 1 over n, so very slow convergence. But with that calculation extremely accurately to within 1%.
Yeah.
Yeah. So did you ever check this? For the
Yeah. We have checked the extrapolation. You have to get still quite far. You have to get still quite far. It's still
surprisingly accurate in a sense.
Yeah. You can do, but still you have. I don't remember exactly how many units we had to reach, but I remember how much time I waited for this calculation to complete before that the extrapolation was actually reaching the periodic result. So it's
then more technical in the sense for all these DFT calculations, you didn't really give many basis sets. So what are the basis sets you use in these systems? Because it's always what to think about. I mean, you very easily get all the complete basis sets, so then you have to fiddle around. Is that?
Yeah, of course.
What is the situation today?
Okay, so of course the problem of basis set is a serious problem because there are no standard basis sets for solid state, and I think it will be difficult to have some standard basis set because in the solid state you have a much larger variety of chemical situations that you have in molecules. So if you think of metallic system, ionic system, covalent system, molecular system, they are totally different chemical situations. So the same element, in a sense, cannot have the same basis set in all these kind of different situations.
Are you saying that you fiddle around every single time?
Yes. No. But the point is that I want to make is that the critical point is not the overcompleteness of basis set, because you can always remove, we have tools for removing the linear dependence in the system. So the point is not the basis set becomes overcomplete. The problem is that the distance you have to go before, so the problem is that Coulomb series are not converging, right? So if you are doing Fourier transforms of Coulomb series, they are not converging. So you have all kind of tools that are implemented in the crystal code to make them converge. But the more the basis set is diffuse or big, the more these tools are put at stress. And but they might work. So in principle, for non-hybrid functionals, we can handle quite big basis sets. When you come to hybrid functional, the exchange term is a real challenge, because then the exchange term becomes very long-ranged if you have diffuse basis functions. And then becomes critical.
So how is it in these systems? You need less diffuse than we do for molecules, because they help each other. So
exactly, so they are closely packed, so you don't need diffuse functions. A different story is for MP2, where you actually need this diffuse function for the virtual state. So what we do is to use a dual basis set trick. So we converge the Hartree-Fock with a smaller basis set, and then we just add the diffuse function for the virtual space.
How well can you actually saturate the space for virtual excitations? I mean, how much of the correlation energy do you pick up?
We always try to make what best we can, but I wouldn't say, difficult to say exactly what is the converged limit. I wouldn't be able to give a number.
So you don't, I mean, a double zeta would give 60%?
Yeah, so generally we are at a triple zeta quality. Generally.
David had a question first.
I think if I understood well, you said that your Raman frequencies were not scaled.
Yes.
But they should, right? If you use the harmonic approach.
Yeah.
Then you have all those sort of tables with different functionals and scaling factors. Because I mean, if they're not scaled, your final very nice fit with might be an accident, right? In a way.
So in that plot we're not scaled, but I've done also what is published is the one with the scaling, with the scaled version, which actually fits perfectly with the.
Okay,
so that was a bit deep calculation. So you have a factor, I don't know, 0.95 you have to multiply, and then this makes it even better.
So it gets even better with the scaling.
Yes.
When you are speaking of overcompleteness, you mean linear dependence?
Yes.
Yeah. So it's not overcompleteness.
No.
Okay.
In a sense, when you have several atoms doing the same work. So.
More questions from us now? Don't think so. Tromsø? More questions? Yeah, we know.
Yeah, a technical question. What kind of parallelization scheme do you have in Crystal?
So we use a purely MPI protocol. So it's simply MPI. So it's there are two schemes. So one scheme is we have what we call a parallel crystal, which is a replicated memory. And the massively parallel crystal is a distributed memory. So for instance, diagonalization is made such that a Fock matrix is a bit held by each processor, and then we use libraries like Scalapec to make diagonalization across the whole system, so we can distribute the memory, but it's all pure MPI.
Yeah, but I mean, what kind of load balance do you have? Is a simple mass slave or other advanced parallelization scheme?
So if, I don't hear you well. So you're asking for about load balance, right?
Yeah, is static load balance?
Master slave or some more intricate way of it?
No. It's there is all machinery, that takes into account that the load of all the processor is as balanced as possible. So that usually we don't have problems of load balancing. So if you look at this calculation on 2,000 cores, then in the end, the work done by each processor is approximately the same.
Yeah, but I don't think I got the answer.
I don't hear you well, so I didn't hear you well the question.
So I mean, like in Dalton, I guess also in S Dalton, the parallelization scheme is a mass slave. The central node distributes the task to each slave or work node. I mean, I wonder what kind of scheme in Crystal.
No, it's not a master-slave. It's like the tasks are distributed, but they say all processors work in the same way. I think I wouldn't call it a master-slave scheme, but I don't know what is exactly the definition of a master-slave scheme. So I'm not sure that what I'm saying is right.
I guess if one master tells all others what to do, it's a master slave. And,
yeah, then I don't think it's like that.
All data.
Yeah, well, the data you have to collect in the end is
Very small.
Is very small because
So it doesn't matter that much.
yeah, exactly.
What you call embarrassingly parallel.
No, I wouldn't. No, it's not embarrassing.
A lot of processes work, and then only at the end they need to communicate.
Well, there are two parts essentially. So one part is the integral part, which is embarrassingly parallel because each processor computes his own integral and makes his own bit of Fock matrix build, and then there's no communication there. Then there is the diagonalization, which has a lot of communication between processors because this is done through SCALAPAC. So you have distributed memory diagonalization, and all the processors at once diagonalize the same Fock matrix. And this has a lot of communication. This is actually the blocking step when you go to larger systems.
Okay, so let's thank the speaker again. Next week, presentation is from Oslo. We have 2 speakers here, and then following that, it's from Tromsø. Okay, so.
Well,
Thank you.